today we are gonna do another question, which is obtain the dimension of specific heat capacity, and gravitational constant, big G. So to solve this, here, first of all, let's solve it for specific heat capacity, where which is represented by the symbol S. We know that, at least I know, you will know in a later date when we learn about this topic, that heat, Q is heat energy, is equal to mass of the object, the specific heat capacity of the object, and the change in temperature. So this is the heat generated or heat gained or heat lost. This is heat energy, mass, specific heat capacity, and change in temperature. So that means S will be Q by m delta theta. So now we know the dimension of all of them, so let's write the dimension. So as you can, so here, the dimension of Q is the same as that of energy, which will be ml squared t minus 2. Then the dimension of m, which is the mass, dimension m, which is the mass, will be m. The dimension of delta theta will be k. Since it is change in temperature, it will still be in temperature scale. So for example, if I had 1 degree Celsius minus 0 degree Celsius, it will be, let's not do it like this. Suppose we had 20 degrees Celsius minus 10 degrees Celsius, we will still get 10 degrees Celsius. Even though this is a change, there is still a unit of temperature. That's why the dimension of delta theta is Kelvin, since Kelvin will be representing temperature. So now, so we have to find the dimension of S, which is specific heat capacity. So now, since the relation is physically valid, or which is a physical relation, the dimension of LHS must be equal to the dimension of RHS. So it will be Q by m delta theta. The dimension of S must be equal to the dimension of Q m delta theta. So now let's solve it. So here, the dimension of Q is ml squared t minus 2. Since it is heat energy, the dimension of m will be m. The dimension of delta theta will be k. So we get the dimension of specific heat capacity to be, let's see, m and m cancel out. There will be L square t minus 2 k per Kelvin. So k to the power minus 1. So this will be the dimension of specific heat capacity. So let's write the dimension of specific heat capacity will be L square t minus 2 k minus 1. That's why if you search up the dimension of the unit of specific capacity, in this case it will actually be meter square per second square per Kelvin. So per Kelvin. So this is actually the unit of specific heat capacity as well, but we don't need that right now, so let's remove this. Okay, so we just found the dimension of specific heat capacity, which was L square t to the raised to the power of minus 2 and k raised to the power of minus 1. So now let's do the second part, which is, so here, for gravitational constant big G, let me change the color of this one as well. since this is kind of a topic of the question. So let's go here. For z, we know the formula, which is f equals to z m1 m2 by r squared. So g, isolating g, will lead us with f d squared by m1 m2. Now the dimension of force is mlt minus 2. The dimension of d and the dimension of r. So d and r and d are similar. So in various books you will see sometimes here r, sometimes d. So the dimension of r, in this case, it is not radius, it is the distance between the two objects, will be l, since the distance is a length. Then after that, the dimension of m1 will be equal to the dimension of m2, since both are masses, and this will be the dimension. So now let's find the dimension of big G. So since the relation is valid, the dimension on left hand side must be equal to the dimension on right hand side. So we can write Z must be equal to f r square by m1 m2, and its dimension must be equal to the dimension of G, where this is supposed to be a square bracket, don't mind the round brackets. So now the dimension of force is mlt minus 2. The dimension of r will be l squared. The dimension of m1 will be m, and the dimension of m2 will be m. So in conclusion, we have that our G will have a dimension of let me add. So here G will have a dimension of, let's look at mass. So mass m by m squared, which will give us m to the power minus 1, L times L squared, which will give us L to the power cubed, and T minus 2. So therefore, the dimension of gravitational constant big G will be m minus 1, L cubed, T minus 2. So that's it for today's video. In the next video, we are gonna do another question.